Prim's algorithm is a graph algorithm for finding the minimum spanning tree of that graph. But what does that mean? What is a minimum spanning tree? Let's say we have 4 towns or villages or whatever, and currently we don't have any roads between them. So if I'm in village B, I can't see my friends and family in village A. Well, if we want to install some roads, how might we do that? How can we choose which roads to put in? So, for example, ideally, from every village, we would be able to get to every other village directly, just like this. If I'm in village B, I can go to A, C, or D. If I'm in village C, I can go to B, A, or D. That's brilliant because I have a direct route to everywhere. But if you can see, we've got a lot of roads now. We've had to build a lot of roads. We've had to build 6. And maybe we just can't afford that. That's a lot of roads to install, and it's also going to take a long time to build. But what if we were to get rid of this one, and this one? Well, now we can still get from any village to any other village. I can get from A to B. I would have to go through C and D, but I could get to B. Now, at this point, we need to decide what we are going for. Do we want to minimize the travel distance for anyone going between any 2 villages? Or do we want to minimize the amount of road that we're going to build? And another thing to consider is if this is a weighted graph, maybe the distance between B and D is, say, 5 miles, but the distance between A and B is maybe only 4 miles. So in that case, we would want to build the road from A to B instead of from B to D. But then we don't want this road here as well, because then we've just built an extra road and we don't need to. So a minimum spanning tree is a subgraph being another graph where we don't have any more nodes or any more edges. We have fewer or the same amount of edges and the same nodes. A minimum spanning tree is a subgraph or just a graph with some edges stripped out, where we can still get to every single node from any other node, directly or indirectly, but where the total weight of all of the edges is the minimum we can possibly make it. And in some cases, there are going to be multiple different options. So maybe let's make this 8, and maybe the distance between A and D and C and D are both 2 miles. They're the exact same. In this case, this would be a valid minimum spanning tree, and so would this. It doesn't really matter as long as we have the minimum possible road to build. There are a few different algorithms that we can use to calculate the minimum spanning tree of a graph. You've got Prim's algorithm that we're going to be looking at today. You've also got Kruskal's algorithm and Borufka's algorithm, if I'm saying that right, which I'm definitely not. But we move on. Different algorithms are going to be better or worse in different scenarios, depending on how many nodes you have, for example, versus how many how many edges you have between each of the nodes. But yeah, today we're going to be looking at Prim's algorithm. As you can see from this button up here, the first thing we need to do is make a connected graph. We need to have a graph that from any node you can reach any other node either directly or indirectly. So let's make that. Let's make a connection between these two, and you can see that we're also using a weighted graph. This will become a lot more apparent shortly. And as we make a connection to village D, you can see this button changes to select. So we need to select a starting point for Prim's algorithm in order to find the minimum spanning tree. We're going to start at one point and expand outwards. If we select a village for now and hover over start, it's going to give us a little message down here to tell us that we may want to change the weights of every edge, because that will make things a bit more interesting. Another thing that will make things a bit more interesting is if we have a few more edges at all. So maybe we have something that looks like that. And let's change some of the arcs, so edges rather. So let's have maybe 2, and then 5, 8, 10, and 12. Okay, so let's go back to B. Now when we hover over, we don't get that message to tell us to change some of the weights. So let's click on start, and we can start to go through what Prim's algorithm, how it works. So the rule in Prim's algorithm is we want to find the shortest the shortest edge that connects a node that we've already visited to a node that we haven't already visited. So B is our starting point. We've visited this without even having to do anything because it's our starting point. We haven't visited any other node. Another thing I should add is that we want to visit every single node. Once we've visited all of the nodes, we know that we have found the minimum spanning tree. So the first thing we need to do is we need to connect B, or our starting village, to another node that we haven't visited. In which case, B is the only one that we have visited, so we can choose anything. So we've got our options here. We've got this edge of weight 2 and this edge of weight 8. Well, obviously 2 is less than 8, so we're going to take this edge here. So if we click next, you can see that this bit becomes highlighted. Okay, so now we've visited 2 nodes. We've visited B, we've also visited A. So now we need to go back to our rule. We need to find the smallest edge that connects a node that we have visited to a node that we haven't visited. And now we have 3 options instead of 2. We have this one again, connecting B to D with a weight of 8. We have this one here, connecting A to D with a weight of 5, and then this one here, connecting A to C with a weight of 12. Now we've got 8, 5, and 12. 5 is the smallest, so we're going to take this one. And now we're going to see something a little bit more interesting. We still stick to the same rules, but now we need to be a bit more careful. We want to find the smallest edge that connects a node we have visited to a node that we haven't visited. So we check all of the nodes that are the edges that are connected to our visited nodes. So we've got this one from B to D. We've got this one from A to C, which is 12, and this one was 8. We've got this one from D to C, which is 10. So we've got 8, 10, and 12. The smallest here is 8, but it connects nodes B, which we have visited, to node D, which we have also visited. So we just ignore this one. We don't want this one, because if we were to add it in, if we were to make a road between village B and village D, then we would have 2 ways of getting from each of these 3. We don't want that. We want the smallest amount of roads possible. So even though this is the smallest edge that we have left in the graph that isn't being included yet, it's not going to be very useful to us. It's going to create what's called a cycle, which is where you can return to the same node without traversing an edge more than once. But going back to this, the 8 is no longer an option, so we just compare the 10 to the 12. And of course, 10 is shorter, so we're going to take this edge from C to D, or D to C. And now we've visited all of the nodes in the graph, so we can finish the algorithm. We know that we've finished because we've got our minimum spanning tree highlighted here. And that's all there is to Prim's algorithm, but let's just have a look at a different example. So let's finish this up so that we can return to editing. Let's maybe add an edge between these two and start changing some of the values. So maybe this is going to be a 9. This can become 15. Change this to 4. This to 3. And yeah, let's go with that. And let's start from D. So we click start again. And because this is the first node, it's quite easy. We just look at all of the edges connected to D. 4 is going to be the shortest, so we go over to C. Now we see everything that is connected to C or D. So the 15, the 9, the 8, or the 3. We go with the 3. And now we go for the shortest connected to D, C, or A, which is this 2, the 15, the 9, or the 8. The 15 isn't going to be useful to us because it's connecting two nodes that are already connected, but it's 15. It's not the smallest. In fact, it's the largest, so we don't care about that at all. The shortest is the 2 over here. And now we've visited all of the nodes, and we've got a minimum spanning tree going around the edge like this. Algorithms like Prim's algorithm and Dijkstra's, which we'll be looking at next video, are kind of scary once you first get into them, mainly because they're quite difficult to write out as code. But if you really take the time to understand what's going on, and you can see how the algorithm is working and break it down step by step, it becomes a lot easier. So I'll see you next video when we talk about Dijkstra's algorithm.